All right, question 21 on GRE practice test 1 here in section 5. We have another problem where we're supposed to analyze information from a graph. Although now our graph is not this chart dealing with the caffeine content of various drinks and drugs. It's instead this chart, which is kind of an interesting chart. Talks about the energy used per meter and the speed that you're going when you're running and you're walking. So lots of information being captured on this chart right here. It's probably worth your time to spend 30 seconds or so familiarizing yourself with this, getting an idea of how it reads before you even read the question. So note that here on the y-axis, we have the energy that's being used, and here on the x-axis, we have the speed. Oh yeah, that makes sense. As the speed changes, the energy that you're going to use is changing. But we don't just have one curve here on our graph, we have two different curves, because we're studying the relationship between the speed and the energy used, not just for one activity, but for two different activities, walking and running. So looking at this walking curve right here, it looks like when my speed is pretty low, when I'm on the left on the graph, the energy that I use is pretty low. I'm kind of far down on the graph. But when I go to the right, my speed gets faster and faster and faster. I go up, the energy that I'm using is more and more and more. Yeah, that kind of makes sense. Interestingly, maybe running is a little bit different. If I'm running really, really slowly, I don't know how you'd run 2 miles an hour, but I guess if I was doing it, I'm not really efficient. In fact, I can speed up a little bit, speed up all the way to 4 miles per hour and use less energy. And you're like, whoa, wait, how's that possible? Well, it's not just the energy used, it's the energy used per meter. So if I speed up, I'm finishing those meters more quickly. So I have less time to kind of use up my energy. Whatever, none of that is relevant. Just an interesting characteristic of this graph. I don't like both graphs being black, so now I have one's red and one's black, whatever. So anyways, finally getting to the problem. S is a speed in miles per hour, so we're talking about the x-axis here, at which the energy used per meter during running, so the height, the y-coordinate of the red line, is twice the energy used per meter during walking, so the y-coordinate of the black line. Then according to the graph, S is between. So what speed is the red graph twice as high as the black graph? Well, I only have values on the black graph up to 5 miles per hour, so it's certainly not anything over here. And for these speeds close to 5 miles per hour, just by looking at it, you can tell that red is not twice as high as black. So you might be able to just look over here and kind of ballpark the speed at which the red graph is twice as high as the black graph. But if you have a hard time just ballparking that, you could do things more concretely by looking at the energy used at each of these different half-mile-per-hour increments of speed. What I'm saying is, even though these half-mile-per-hour increments of speed start at 2.5, I'm going to start at 2 miles per hour because that's the furthest left point on the graph for which I have energy used for both walking and running. If my speed is 2 miles per hour, the height of this black graph is, I don't know, like 140 or something. Some number a little bit less than 150, but definitely more than 100. If I take that 140 and double it, I get 280. So if my running energy used at a speed of 2 miles per hour was 280, then 2 would be my speed S, at which the energy used running is twice the energy used walking. Unfortunately, it's not, because looking at our graph here, the running energy used is more than 300. So since this is less than 150 and this is more than 300, this is more than double this. So S does not happen at 2 seconds. We kind of already knew that by looking at the answers, but by talking that out, it'll be easier to figure out which of these the actual answer is. The next speed that I'm interested in is 2.5 miles per hour. This gets a little bit hard to read on the graph, but we'll end up with the exact same conclusion. At 2.5 miles per hour, the energy used is still less than 150. I don't know, maybe now it's 145 or something when I'm considering walking. And the energy used when I'm considering running appears to be exactly 300. So I'm still in the case where running is more than double walking in terms of the energy used when I'm at 2.5 seconds. What about 3 seconds? Well, at 3 seconds, it looks like the energy used walking is, I don't know, this is a little hard to read, maybe exactly 150 or ever so slightly more than 150. But when I consider the energy used running, now we're less than 300. So double 150 would give me 300. I'm less than 300. So the energy used running is less than double the energy used walking. Maybe that's worth writing down. When I was at 2.5 miles per hour, the energy used running was more than double the energy used walking. But at 3 miles per hour, the energy used running is less than 2 times the energy used walking. What that tells me is that at some point between 2.5 miles per hour and 3 miles per hour, technically because these graphs are continuous, the energy used running was exactly equal to twice the energy used walking. A must be my answer. The way the problem's written implies that there's only one point at which this happens, so we don't have to go searching for other answers. But maybe in some other problem, I might read a little bit different to allow there to be multiple different values of S. If that were the case, you might want to rule out these remaining answers. One way that you could do that pretty quickly is recognize that anytime our speed is more than 3 miles per hour, so anytime we're to the right of this green line, the energy used running is less than 300. So anytime we're to the right of this green line, but to the left of this brown line, because to the right of this brown line, we don't even have data on walking because you can't walk that fast. The energy used running is always less than 300, and the energy used walking is always more than 150. So double 150 is 300. This is always less than 300. This is always more than 150. The energy used running can't possibly be equal to twice the energy used walking.